Hi, this video is for Friday the 26th of February, class number 15. Just a couple of announcements to begin. Remember that homework number 5, which has those questions related to the Hardy-Cross method and a little bit of coverage of water hammer and surge tank, that assignment's due before class on Monday the 1st. And then the following assignment, homework number 6, which is covering pumps, which is introduced in today's class meeting, that assignment is due on Monday the 8th of March, and that's going to be the same day that we have our first midterm exam. And so in today's class meeting, we're going to be covering a little bit on surge tanks, which we didn't get to in class last time when we were discussing water hammer. So we'll finish up with surge tanks and then also talk about pumps. And the pump coverage comes from chapter 9 in the textbook. And then we're also going to get a little bit of practice having to do with an additional Hazen-Williams equation question, just to get you ready for that FE exam that's going to be here before you know it. I'll just reiterate what I say all the time. If you have questions on the material or the homework, anything at all, feel free to reach out. You can contact me via email, give me a call, contact me on Teams. I'll do my best to respond, and if you have any questions, get in touch. Have a good one. We'll be back in person on Monday, March 1st. We'll have a live lecture at our normal time.
Surge tanks are one of the ways to relieve that shock wave and to give some place for the water to go so that the pipe doesn't have to expand. So it's kind of preventing the water hammer from ever occurring. And a surge tank is just a reservoir. In this case, it's depicted just as like a branch pipe. And you essentially remember that more water went into the pipe when it was all the way expanded. Back in the case of here, those dashed lines were representing the fact that some additional water had gone into the pipe as the pipe expanded. And so rather than allowing the pipe to get so much embodied energy and then later on contract, what the surge tank does is just give it an alternate location for the water to go into. And how high the water surge is going to be depends on the length of the pipe, the area of the pipe, the cross-sectional area, and then the diameter of the surge tank is going to affect the cross-sectional area of the surge tank. And so if you have a very large diameter surge tank, then the water level isn't going to go up or down very much during a surge. But if it's a relatively narrow surge tank, then it's going to have a lot more height to it for the water to fill up that volume. So let's take the same case that we just were solving, where the physical length of the pipe is 2,000 feet, 4-inch inner diameter, and the flow velocity that we know. How big around, what would the diameter need to be for a surge tank if we only wanted the water depth to increase by a maximum of 1 foot during the surge? So in other words, solve for the diameter of the tank, which is going to go into the cross-section of the tank, assuming an S max of 1 foot. So I was glad to hear your skepticism. People were saying 18 feet, that seems like a lot. That's pretty big. So that means you're thinking in terms of reasonableness. It is that big, but that you're evaluating things against what seems normal. You know, that's just a 4-inch diameter pipe, right? But think about the volume of water in a 4-inch diameter pipe over 2,000 feet. It's a lot of extra water that's going to be in there. So if we didn't want to make a tank that big, then of course we just have to make it taller. But either way, there's a certain volume of water that has to be contained during that surge, and if we provide a place for the water to go, then it relieves the pipe of the necessity of expanding during the surge.
Pumps are a way of adding energy to a system, and the simplest form of a pump is a positive displacement pump, which lifts the water physically, and the way that it adds energy is in the form of potential energy. And so remember that when water is in a system, the energy can be in one of three places. The energy can be in the velocity head term, meaning that the water is moving through the pipe, so some of the energy is in its motion. Some of the energy has to do with its elevation, so the Z term in the energy equation, and then some of the energy is the pressure, and so the pressure head term. The way that a positive displacement pump like this open screw pump is working is by lifting the water. And you can see that it doesn't have any way that it could be adding pressure because it's open to the atmosphere. Now this is at an angle. That's kind of implied by the fact that you can see, it's narrower at the top, and so it's at an angle. What it's doing, it's lifting water out of a canal, and then it's dumping it into a trough, and then it's flowing by gravity from there. So it's a screw pump. And it's adding energy by adding Z. Now there are other positive displacement pumps that, this is supposed to be animated. There it goes. This illustrates that in the case of a positive displacement pump, with each rotation, a constant volume is delivered to the destination. And whether it's a rope pump, which has a series of plugs at the end of a rope, and each plug makes a seal with the surrounding well casing, and then as the plug comes up, it's lifting the water, and then it's dumped out into wherever it's headed. In an internal gear pump, you can see that as it rotates, the water is taking up the space between the gears, and it's here that the water could be pressurized and delivered downstream. So in each of these cases, a peristaltic pump is pretty common in environmental science and chemistry, because what they'll do is they'll have flexible tubing coming in and going out, and so as this rotating wheel presses on the tubing, it forces a certain amount of liquid to the discharge side, and then it's sucking it in on the inlet side. So each one of these, with each rotation, is delivering a certain volume of water. These are all pretty non-common pumps. I mean, in municipal applications, you're not likely to encounter one of these. These are more specialized applications, like maybe in a low technology irrigation setting or in the lab. But more commonly, what we would see in municipal water delivery is a radial flow pump. And a centripetal flow pump is going to be adding energy by accelerating the fluid and increasing the pressure. Inside the pump is a series of blades that are shaped like a wing. If you look at the outside edge of that shape combined with the length of it and the angle of it, have a way of accelerating the fluid, creating a difference in pressure on the upstream versus the downstream end of the impeller. And it's also changing the direction of the flow as it comes in at one angle and goes out at a 90-degree angle. Sometimes pumps are, they would say pump when really it's a motor and a pump, but strictly speaking, the pump is just what is turning mechanical energy into fluid energy, and the motor is doing something separate. The motor is turning the electrical energy into mechanical energy. Closely related to this radial flow pump is an axial flow pump. It's doing the same thing in terms of accelerating the fluid and increasing the pressure, but it's just that in the case of an axial flow pump, the motor may be at the surface and the impeller would maybe be submerged underground, perhaps quite a distance. The shaft length could be pretty long, whereas in the case of a centripetal pump, there may be a suction hose that goes down underground, but it would be less common to bury this entire system, whereas in the case of an axial flow pump, you could have the motor at the surface where it's getting electricity and it can cool off, but the impeller could be down underground, like pumping groundwater up from beneath an aquifer. But in this case, it's adding energy in the same way. It's increasing the pressure. One of the things that we're going to talk about when we look at the pressure that's being added by a pump is the risk of a phenomenon called cavitation. And cavitation is where the vapor pressure of the liquid is based on the temperature, and it's the pressure below which the water will begin to boil. And you may remember the videos that we looked at in fluid mechanics where if you have a vacuum above the water can begin to boil even when it's not heated. We can have a similar problem occur in a pump system like this, where we know that atmosphere, the water in contact with the atmosphere means that in gauge terms the pressure is 0. In absolute terms the pressure would be 101,325 pascals here. And so the pressure is approximately equal inside of the suction side, but as you work towards the pump, the pressure is going from 0 gauge and now it's dipping into negative pressure. And so it's not negative absolute pressure, it's negative gauge pressure. In absolute terms you're still positive, but the closer you get to the vapor pressure of the liquid, the higher the risk of cavitation is. And inside the pump itself, by those blades, the pressure can drop low enough that there is vaporization of the liquid water into a gas bubbles. And so one of the things in pump operations that we'll calculate in class probably Wednesday is the risk of cavitation. But it is something we need to be aware of, that although pressure is being added in the pump and the pressure is high on the downstream end of the pump, on the upstream end of the pump where the water's coming from, the pressure may be relatively low. And so the strategy that's used to eliminate or reduce the risk of cavitation is, number one, you don't want to have a very long suction side pipe. And then the other thing is you want to minimize the elevation difference between the reservoir and where the pump is located. Because if you have an elevated pump that's really high above where you're sucking the water from, then that's another thing that can reduce the pressure in the suction side hose. Okay, so recall the pump equations that we've seen before, where the power in terms of watts is calculated by the flow rate through the pump in cubic meters per second, the unit weight of the liquid in terms of newtons per cubic meter, and then the pump head that is being added. And the pump head has units of length, so meters. And what comes out of that is watts. And this is the ideal pump equation when we haven't yet factored any efficiency into account. Of course, the British gravitational system has traditional units of horsepower if you divide by 550 foot-pounds per second per horsepower. Now, the overall efficiency of the system takes into account both the efficiency losses having to do with the motor, which is turning electrical energy into mechanical energy, and the pump, which is turning the mechanical energy into fluid energy. And so the real pump equation, where we are taking into account the efficiency, is going to tell us the amount of power required, how much electrical power is required to go into the pump in order to provide a desired amount of pump head. And so this would give us how many watts is required, and you'll notice that we're dividing by the efficiency factor because the losses increase how much energy we have to put in to get out a desired amount of energy, of fluid energy. The pump's efficiency, we usually would look up off of a table that's provided by the manufacturer. And manufacturers have done lots of calibrations and calculations that characterize the efficiency of their pump under a range of flow rates for a variety of different liquids and diameters. And so it's not just as simple as always being given a single efficiency factor, like I'll do in our example problems just to simplify when we're focusing on other concepts. But in reality, the efficiency of the pump changes depending on the flow rate. So you may have a pump that's really efficient at a certain flow rate, but then if you turn the pump down, then its efficiency drops off considerably, and so you're requiring even more electricity than you would have at a more stable operating point. And the reason why we have efficiency factor is that there isn't 100% conversion between the electricity and the energy that gets into the water. There's energy losses having to do with the pump and the motor. Both are heating up, so there are heat losses, friction inside the pump. The pump may not be perfectly sealed, and so that there are losses there as well. Turbulence inside the pump. So a manufacturer, like I mentioned, has gone to great lengths to characterize the performance of their pump, because they want their customers to be able to buy a pump that works in the system that they have in mind for it. And so what the manufacturer does is they'll describe this curve that says for a certain flow rate how much pump head that pump is able to add to the system. And so remember that the pump head is a term that goes into the energy equation. In the energy equation we have P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus H sub P is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus HT and HL, where HL is the head losses due to friction and also due to local losses. Now, a turbine, you're not going to see turbines very often. A turbine exists at a reservoir, but a turbine isn't going to be in a municipal water network just between the drinking water treatment plant and someone's house. So usually we can just assume that there's no turbine in the system unless we're doing a hydropower application. And so in the energy equation, if you're looking at here is point A and there is point B, and you know how much pressure you want to deliver at the destination, and you know how much losses there are going to be between here and there, what you'll be solving for in the energy equation is how much pump head is required to get the water to flow from here to there. And once you calculate that pump head, then the next question is, well, which pump do you need, and how much electricity is that pump going to be consuming? And so that's where these pump curves come into play. Is this curve is telling you for a certain flow rate how much pump head you can expect to see. And there's a cutoff point where it's the maximum amount of head it can provide is at a low flow rate. But then as the flow rate that's going through the pump increases, then it generally isn't able to provide as much head at higher flow rates. So the pump is working against a head, that is the losses and the elevation differences. That's what the pump is trying to overcome, is the resistance to flow between here and there. And it's adding energy, but as the head increases, then the pump flow rate decreases. So this can usually be expressed in terms of an equation. These curves, like where the intercept here, in this case it says 24.4, that's the maximum amount of head that the pump could add if there was no flow rate. But then as you start increasing the flow rate through the pump, then it's not adding as much pressure. And remember, the way that it's adding head to the system is through an increase in pressure. So if you're turning the flow rate up on the pump, it may be increasing the flow that's going through it, but its pump head is progressively going further and further down. So that's one side of the coin. In a system of figuring out what's actually going to be the flow rate, one aspect of that is the performance of the pump that's been added into the system. The other side of the coin is that you have to come up with the energy equation, some representation of what the system itself looks like. And so in this illustration, what it's showing is that water is being lifted from a lower reservoir and is being pumped up to this upper reservoir. And along the way, we're overcoming friction losses. It looks like there's a couple of pipe bends there, and so there would maybe be local losses that it would be overcoming. There's a delta Z, and so we could, when we have a picture of the system or a description, we could come up with a system curve. Now this is different from the pump curve that I just showed you. And the characteristic of a typical shape of a pump curve is that there's an intercept and then it's sloping downward. That's the pump performance curve. The system curve has an intercept as well, but then the curve is going up, because what this represents is the amount of pump head that's required to achieve a certain flow rate. And the curve is getting higher and higher at an increasing rate, because what we know is that the head losses are increasing as the flow rate goes up by squared power. Now this system curve is just rearranging the energy equation, where we're assuming that at both the origin and the destination there's no velocity. So if we cancel out the velocity head term, and here at both the origin and the destination it's open to the atmosphere, so they've canceled out the pressure head terms. And so what we're saying is the pump has to add enough energy to overcome the elevation difference, and then it's also adding energy to overcome the friction losses and the local losses. And so this is the system curve, and it's a function of the flow rate squared. Even though, remember, the Darcy-Weisbach equation that we use a lot, H sub F is FLV squared divided by D2G. Well, we're getting pretty accustomed to the idea of instead saying FLQ squared divided by D2GA squared. And that's equivalent. And that's what this is doing, is it's because we have the pump curve in terms of Q, not in terms of velocity. We're going to be setting these two curves equal to each other and solving for the flow rate Q. And so we want to express both the local losses and the friction losses in terms of flow rate. Any questions? Here's the two curves overlaid on top of each other, and the operating point, you know, when you put a certain pump into a certain system, it's going to achieve a flow rate where the two curves intersect. That's the operating point. And the thing that makes it tricky is that we don't know what is F until we know Q. This is the same dilemma we have a lot, where you don't know the friction factor until you know the flow rate. And so the assumption that we start with when we're solving problems like this is the fully turbulent flow assumption, that the Reynolds number, the velocity is high enough that makes this Reynolds number big, and this term of the equation is insignificant compared to the relative roughness term. So we'll start with that assumption, and then we'll check it later on when we're doing calculations. Okay, so here's an example. We have a system curve. Now this is just the energy equation that I've rearranged in terms of H sub P being the unknown. And let's say that we have this pump. We have a pump that if we have zero flow rate, it can add 24.4 meters of head. But then as the flow rate goes up, it's adding progressively less and less head. So there's some equation that describes the pump curve. We'll have to come up with our own system curve with this given description. It looks like we have 120 meters of length of pipe. We know the diameter of the pipe, the equivalent sand roughness of it, some local losses, and then the elevation difference that we're lifting from one tank to another tank. So let's find out what flow rate would exist if we substitute all of these variables into both equations, and then we set H sub P of the pump curve equal to H sub P of the system curve, and our only unknown will be Q. So we're going to be solving for Q with those two curves. And for this one, you will use the fully turbulent flow assumption and then check it to see if it's valid by calculating a new updated F after you determine the flow rate. Okay, so I show you the development of the system curve up on the screen there if you want to compare what you've been calculating to what I've got. The major components of the system curve are the elevation difference, the friction losses, and the local losses. So we can get an idea of the relative magnitude of each by looking at, all of these values together. 198 gives you the sense that the friction losses are about 4 times more important than the local losses here in the resistance that exists in the system. So if you set the system curve equal to the pump curve, then the flow rate we ought to get out of this is about 0.244 cubic meters per second.
It's like a cadence.
So once we have a flow rate, then we check the fully turbulent flow assumption by getting the velocity, calculating the Reynolds number, and putting that into the full Jane equation without this crossed out. And what you get when you do that is that the F value is 0.01995. So using our updated F is 0.01995. So the question is, how does that compare to what we originally assumed with the fully turbulent flow? Our original assumption was 0.096. And so comparing 0.0196 to 0.01995, that's about 2% different. I mean, if it really counts down to the last hundredth of a cubic meter per second, then we may need to do this over again, and instead of using the 0.0196, substitute in the new better guess for F. But it's ultimately going to change the flow rate about the same as the F value changed, maybe actually a little less, because we didn't change the local losses. So the flow rate, even if you recalculate this again with the updated F value, it's going to be about 0.24 cubic meters per second. But we do need to check it. In this case, about 2% difference tells us that's close enough. The main thing is just getting a feel for how you set a system curve equal to the pump curve and find the operating point. And by the way, we can solve this graphically using Excel. I wonder if I have that in there. So for the system, we can put in the equation for the pump curve and just put in a bunch of different flow rates. And so these flow rates, it's just across a range. So we would have the pump curve as a function of flow rate, and then we could have the system curve as a function of the delta Z and the losses that we know about. And so in the end, you could do a graph that includes the known pump curve, the system curve, and finding the operating point for, at what point is the difference between this pump curve equation and the system curve equation, at what point is the difference 0? And so we do a little like goal seek, and you'd find what Q gives you the difference equal to 0, and that's the same operating point that we just calculated by paper. But it's kind of a graphical solution that illustrates the same effect. Any questions about pump operation point? Okay, so with our 14 minutes that remain, let's do an additional practice Hazen-Williams problem. How do you know whether you should use this equation or that one? Because they're both the Hazen-Williams equation, so which one do you use? You use the bottom one, but why?
I don't know what's up.
You don't have SF, that's right. Yeah, we already know the flow rate, and from that we can find the velocity. So it's kind of, I mean, you could use this equation and then solve for S sub f, and then from the length find h sub f, but that would be pretty an indirect route. It's just, you know, what do you have and what do you need to know? And you need to know h sub f because we're going to put that into the energy equation. Good luck on your test.
Thanks.